Okay, so let me talk about molten salt reactors and thorium. I'm running short, so let me go quick. So molten salt reactors can solve the light waste reactor waste problem and safely breed for uranium-233. The best design is the so-called two-fluid design. The Oak Ridge one was a one-fluid one, but we think it's possible to build a better one, which is a two-fluid design. So if you have light water reactor spent fuel, you have mostly unburnt uranium, 238, 235. You have some plutonium that you've generated from the 238. You have fission products. So this is the stuff that's bad. So the only way to get rid of it is not to bury it in a mountain, it's to put it in a nuclear reactor. Okay? Separate out the plutonium, the uranium, and separate out the fission products. The uranium, what do you do with it? Well, you give it to those guys who want to build the sodium fast breeder reactor, or you give it to Bill Gates, who wants to build a traveling wave reactor, and they both can use depleted plutonium. Or if you don't like those, take it to Yucca Mountain. The fission products you can bury. What do? We bury them 6 feet deep, just like we do with people. All right? And they can stay there for 300 years, and then they drop below background. Don't throw it away. There's all sorts of good stuff down there that will be very, very valuable. Nothing is a waste if you use it properly. We have to have a sustainable way. Or if you don't like some of them, you can bury them also in you. So now the plutonium you put into the core of a molten salt reactor has a chain reaction. One of the 2.59, let's say, is used up on average, and the other come out into the envelope or the blanket. In the blanket, you have a salt that contains thorium-232. It captures enough of the uranium, the neutron, to be turned into U-233. And you make the blanket big enough so it absorbs all those excess neutrons. That's the other good thing about this reactor, because not much hits the walls. Remember, I told you, when neutrons hit matter, that stuff becomes activated. Here, it's all absorbed by the thorium before it hits the walls. So you have very low-level waste. Once you got uranium-233, you take it out of the blanket and you put it in the core. And that gives you the breeder, because that continues to give you neutrons. So what is in the blanket? The blanket is a fluoride salt of uranium. Salts are very corrosive, so they will dissolve anything, including uranium, thorium, whatever you want. So uranium fluoride is in the UF4, in form of a liquid. If you just add fluorine gas to it, it turns into UF6, which is a gas. A gas will bubble out of the blanket, and that's how you remove the uranium-233. So you don't have to touch it. It can all be done remotely. You will not only get uranium-233, but you will also get some uranium-232. That's not good for fission. It's even, as you can see. But it decays, and it emits gammas in that decay product. So that's very bad for building a bomb. Bad for the people that try to build it, even if they're willing to sacrifice themselves. It's easy to detect. Even if you were to put in a container port, you could have a Geiger counter. You would know that there's a bomb in there. So no one would choose to build a bomb this way. In fact, no one has ever built a bomb this way, except for one country, the United States. Because at one time, we could do anything. And we built a uranium-233 bomb just to prove it could be done. It wasn't pure uranium-233. It had a lot of plutonium mixed in it. It was a terrible bomb. Nobody would choose to make a bomb this way. It's so easy to make it from plutonium, right? Even North Korea, that's not the most scientifically advanced country in the world. They could build a plutonium bomb. So the challenge here is the breeding. I said on average you get 2.49 neutrons, but when the thorium absorbs it, when the uranium-233 absorbs the neutron, 8% of the time it doesn't fission. It just captures it and becomes uranium-234. Now you've got something worthless. You've got to capture another neutron. So if you count that all in, actually what you have extra after after the chain reaction is only 1.23. If you use sodium fluoride, beryllium fluoride, all these are single isotope things, so they don't like to absorb neutrons, but sodium does absorb a few neutrons. You're down to 1.09. Remember, you have to be above 1 to breed. If you have any fission products around, even if they're only 10% of normal, you probably absorb another 0.03. If you have xenon 135 around, and you're only 10% of that, you lose another 0.03. So you get very close to 1. I'm not sure myself whether breeder reactors can actually be built. Maybe they can be built. If they can be built, we should build them. If they can't be built, it's not clear to me that these reactors are so much better than what we have today. The attractiveness is to get away from plutonium and go on to a pure thorium cycle, in my mind. So let me I'm sorry I'm over time. I will try to finish up. So I've already said that if you overheat, the fuel will expand out of the reaction zone. But there's another safety mechanism. That is, if for some reason the temperature continues to rise, then there's another safety mechanism that Oak Ridge invented. And that is, you have these fuel pumps. This is a graphite core where you drill holes in this way that contains the fuel salt. This way contains the blanket salt. You use the blanket salt to cool the fuel salt. And when they're in the pump, they're well separated. There's no graphite, so it's not having chain reactions. It's only when it's all pumped into this compact configuration that it's having reactions. Suppose something goes wrong, okay, and the temperature continues to rise. Then you melt something that you keep frozen, and it opens up a drain, and you drain it into a dump tank. You don't have to worry about that mechanism failing because hot things melt things, right? You don't need an operator there to do it. This dump tank is air-cooled to remove the decay heat. It's not water-cooled, it's not salt-cooled, it's air-cooled. Why? Because you can lose salt, you can lose water, but you cannot lose air. If you lost air, you have bigger problems in this reactor. Okay? You have two metal walls, and if you have a spill, let's say this thing somehow fails. Well, where's the iodine, the cesium, and the strontium? The iodine is just like fluorine, so it's attached to the sodium. The cesium is just like sodium, so it's attached to the fluorine. The strontium is just like the beryllium, so it's attached to the fluorine. It's not going anywhere. It's being the salt. Once it spreads out, it freezes. You have to maintain the salt at a high temperature. If you spread it out, it has a lot of radiating area, it will automatically freeze. And you design it so it freezes in less than 10 seconds. To remove the other fission products, you do online distillation. We have a reactor on board. We can do any amount of distillation we want. Therefore, we can reduce the amount of fission products, even if it got out, to a very small level. In particular, to a small enough level so that we can remove the decay heat with air cooling without the thing becoming enormous. The solid salt is inert, has low vapor pressure. Go home. Try to smell whether you can smell the sodium fluoride in your toothpaste. You only smell the toothpaste. Okay? Salt has very low vapor pressure. No radioactive gases, no fires, no explosions. You have a thick steel dome, so you have no Chernobyl. You have no Fukushima. And even if you to crash a jet plane in it, it will bounce off the thick steel dome. The 9/11 terrorists did consider crashing an airplane into a nuclear power plant. After studying how strong even today's domes are, they decided it would be easier to attack the Pentagon. Easier to attack the Pentagon than to attack a nuclear reactor building. But even if they were to attack this building, nothing bad would happen. It's very hard to vaporize salt. So it's walk-away safe with no operator intervention. That's what we want. People make mistakes. Physical laws do not make mistakes. You want to get people out of the thing so they don't have to make any decision. What went wrong at Fukushima is that people, in addition to having an inferior design, people made mistakes. Okay, so let me just go through the technology challenges. I won't go through the applications to waste, except to say that we have a mechanism to use, transfer the heat to molten salt so that we can take care of things like garbage, human wastewater, okay, all sorts of things. Okay, the technology challenge is that the molten top fluoride salts are corrosive, especially if you have water impurities in them. But we've done experiments with melting salt with graphite in them. The salt is so corrosive that it cracked the quartz tube once it stopped. It etched it so badly that you can see over here it's actually no longer transparent, but it didn't do anything to the graphite. Okay, the weight didn't change. You didn't lose any graphite, even though the graphite was heated to 900 degrees Celsius. Didn't lose any weight. But it's porous. Porous is the last thing you want when you want to make an airtight or a liquid-type container. So we have to find ways to seal it against the molten salt, to keep the blanket and fuel separate. That's easy. But also to keep the xenon-135 from migrating all over the place. And we think we know how to do that, okay? Our team is working on it. All right, this cross-channel graphite heat exchanger we're having exported to Taiwan to do the experiments, everything except chain reaction. When we're ready, we're going to bring this experiment to the United States and hope the United States builds this thing. Okay, but meanwhile, we're going to do all the chemistry, all the physics, all the mechanical engineering, etc., and make sure we can do everything. So we deliberately built something which is too small to sustain a chain reaction. Otherwise, the United States government will get on our case. We don't have chain reaction, so we use electrical heating as a proxy, and then you need special metal walls. And we hope to use, in the first generation, Hastelloy N. That's turned out to be a problem. Lots of people want Hastelloy N, main manufacturer in the United States. We were refused. China wanted 20,000 tons of it. China has declared this reactor as their #1 priority for the next 20 years of R&D. They were turned away. And basically, the company wants to sell it. The government does not want this material to get loose. We hope we can do it, however, in the States itself. Let me just show you some of the things that you have to think about. You have to make sure you have nuts and bolts here. Okay, you have nuts and bolts in almost any kind of machinery. Those have to be made out of metal. You cannot make it out of graphite. When it's tight, at room temperature, when you tighten it, and now you raise it to 900 degrees C, is it still tight? Well, they better expand at the same rate at all temperatures, and we found an alloy that does that. And that's not Hastelloy N, but we now know the alloy that can do that. It can be immersed in the most corrosive of all fluoride salts, a eutectic mixture of lithium fluoride, sodium fluoride, potassium fluoride. And here's what happens when you do a scanning electron micrograph of this thing. You can see it's untouched, except for places where we suspect the vendor had impurities. Okay? And then you can see it etched it a little bit at those dark spots. We went to a different vendor, and we can make much better boats. So these boats exist. You have to make sure it's compatible. You have these things coming out in different channels. You've got to collect it in a plenum. And when you tighten it, you've got to have gaskets that seal. Okay? Well, graphite is a very brittle thing, so you can't use graphite. You have to use carbon-carbon composite. Fortunately, this company that we work with knows how to do that. The gaskets have to be made out of carbon things. They can be compressed. They can do that. And then afterwards, you've got to make sure to compress it to seal is not going to break. Okay? And that we've tested. Okay. I don't think I'll skip that. Here are 10 reasons for the U.S. to build molten salt breeder reactors. And I hope you can all help on this. Okay? What are the U.S. advantages in this field? We are the only country to have ever built molten salt reactors from Hastelloy N. We are the country with the second most advanced carbon technology. I said during World War II, Union Carbide was better than Siemens. There's no more Union Carbide. Siemens is #1 in the country, in the world today, but Germany has ruled out reactors. So they have a subsidiary in the United States that we work with. They're happy to work with us small fries because they see this as a possibility of expanding their reactor division, which Germany has thrown away with both hands. We are the country with the most experience in handling molten salts, and we have more nuclear waste than anybody. That's what's needed. We've had lots. We have more nuclear power plants operating longer than anybody. China is just getting started. We have a big advantage over China, big advantage over India. Of course, eventually, we should help them build these reactors because global climate change is a global problem. But we should make sure these things are built well and safely. We have large deposits of thorium. There's one mountain pass, which Lewis and Clark expedition went through from Montana to Idaho, that has enough thorium to last 1,000 years of U.S. energy use. What are the molten salt breeder reactor advantages? It's safe, it's secure, it provides sustainable energy for the millennium, it has manageable local disposal of waste. If you only need to bury things for 300 years, you should bury it, not in your backyard, but not too far away. California wants to use it, don't send it to Nevada. Of course Nevada's unhappy. Bury it somewhere in California. If you don't want to bury it locally, don't use it. Okay? It's only 300 years to manage this. It's a solution to climate change acceptable, I think, to most people except Luddites. There are people in the world who think that technology is bad, that we should go to a time where there was no technology. Of course, we can't support 7 billion people or 9 billion people, so those same people say we ought to reduce population by a factor of 10 or 20. And I say, that's fine. Who's going to be the 5% that survive? I think, we have technology. Technology has to be the answer, okay, or part of the answer. It will create many well-paying jobs locally and process heat cheaper than coal and natural gas. I've had slides to show you this, but I won't go through this. Basically, you turn waste into biochar, which then you bury. So you create artificial coal, which you don't burn, but you bury it. And that way you're able to reverse the process where we dig coal out of the ground, we burn it, put carbon dioxide in the air. Now you let plants extract carbon dioxide out of the air, you char it into charcoal with molten salt, and then, which is very fast, and then you bury it. Okay, and that way you reverse the climate change. It's a surefire way to do what is called carbon sequestration. We have a pilot plant that we're going to convert all the waste on one of the islands off Taiwan. It's between China and Taiwan. So let me just finish by saying reversing climate change is still possible, but scientists have to speak up, and environmentalists must stop opposing nuclear power. Realistic energy policy needs science-based assessments, not value-based arguments that stalemate meaningful action. And I would like to compare this situation with the last biggest crisis I remember when I was graduating from college, and that was the Cuban Missile Crisis, which JFK learned a lesson. And he realized we had to have peaceful coexistence. He was talking about peaceful coexistence between the United States and the Soviet Union. But today, we need this between nuclear activists and environmentalists. We are all working toward the same goal. Let's not stalemate each other's actions. So here's what Kennedy said in a commencement speech to American University. He said, so let us not be blind to our differences, but let us also direct attention to our common interests and to the means by which those differences can be resolved. And if we cannot end now our differences, at least we can help make the world safe for diversity. For in the final analysis, our most basic common link is that we all inhabit this small planet. we all we all breathe the same air. We all cherish our children's future. And we are all mortal. Thank you very much.
Thank you, everybody. Thank you, everybody. We have about 20 minutes left for questions and answers. So this is absolutely, but before we head into the Q&A time, if you could do us the honor of drawing a name out of the basket for the winner of the Kepler's $30 gift certificate.
Man Hettick.
Congratulations. I also want to let everybody know that Jeb Ebby, who is from the Thorium Energy Alliance, is here, and he has some materials that he would like to hand out. That's him over there. So if you're interested, see him in the lobby. He has things.